All right. So this is the tutorial. Actually, if you take a look, this tutorial is taken from the test 1, semester 1, session 2013-2014. However, if you take a look, the question is a lot. So that means I did some revision. It's not the original question has been modified. The original test question has been modified, and I include all of the necessary element. That means what is the expecting question relating to the closed loop control. So for me, this tutorial is very useful for all of you to try, and in the final examination, this kind of equation will be asked again. So it's better for you to have a good preparation on it. So in this case, let's take a look on the solution for the given question. First of all, you can see my screen, right?
Yes, sir.
Yes, sir.
All right, thank you for your response. Now, we take a look. The question here, consider the process and disturbance is described by the following transfer function. So in this case, the process transfer function, the disturbance has been given directly to you, GP and the GD. So that means you don't need to derive. So you just use the information given to you. And then here you have the measurement transmitter data. Measurement transmitter data, and then in the form of the table where you have the in and the out. On the right, you have the control valve information, the KV equal to 1. And then the next information is based on the set point transmitter. So you have set point transmitter transmission data in the form of the table where you have the in and the out. All right. So here I would like you to solve the question A1, to derive the closed loop transfer function for set point changes using proportional controller. All right. So this is the question. So we take a look on how we can solve this kind of problem. So now here it does not state either the standard block diagram or alternative block diagram will be used. So since you have only the control valve, you have the measurement, where the measurement transmission data here corresponding to the GM. So this measurement transmission data is based on the GM. You have the GP, you have the GD, and then the set point transmitter. So here the keyword is set point, and then you have the transmitter. That means it will reflect you the KM bar. So where the KM bar here represent the set point gain. So that means in this case, the data is given in the form of the table. So based on the question, it asks you to derive the closed loop transfer function for set point changes. All right. Now, if we recall, you have two types of problems, the set point changes or disturbance changes. Since in this case, there is no GIP. So here the GIP, the transducer transfer function is not given. So meaning that standard block diagram will be used. Normally, the information will be given like this, either in the form of the sentences or based on the table here. So let's say the GIP is not given, then that means you don't need to use that one. So here, since the GIP is not available in this question, then we will use the standard block diagram. When you have the standard block diagram, then that means the default equation will be y prime s over y prime SPS equal to Km bar GC GV GP divided by 1 plus GM GC GV and GP. So this is the standard closed loop transfer function for set point changes. So since it does not require you to obtain this transfer function, then we just use directly. What you need to do is to substitute the transfer function. So in this case, we start one by one. Here, the Km bar. So the Km bar is given in the form of table. We know that the Km bar in this case referring to the gain. Gain for set point. I put it here SP, referring to the set point. So in this case, they have the information in the form of the table. Then that means you need to use the formula. So you have the formula of the gain, delta output over delta input. The difference of your output data divided by the difference of your input data. So here you can see there will be the information out and the in for the set point transmitter. So that means you can use the data right away. So for example, here 20 minus 4 divided by 6 minus 2. So that means you need to take it the data based on the difference. Or if you rearrange like this, it's also acceptable. 4 minus 20 divided by 2 minus 6. Also acceptable, no problem, as long as it is the difference. So for this part, the Km bar 20 minus 4 is 16. 16 divided by 4. So you get 4. So this is the value of your Km bar for the set point transmitter. Any question so far?
No, doctor.
Okay. So if no question, then I proceed. So we complete the Km bar here. Now we go for the GC. So GC is available in the numerator and denominator. So for this part, the proportional controller will be used. So by default, your GC will be GC equal to KC, where GC equal to KC represent the standard form for proportional controller. In this case, the value KC is not given. So do not assume yet. Do not assume KC equal to 1 or KC equal to 10. Just leave as it is. So GC equal to KC, we complete that. Then the next is GV over GV. So you have the GV in the numerator and denominator. So GV here, based on the control valve, where it states that KV equal to 1. So in this case, automatically the GV equal to KV equal to 1. So that means in this case, no time constant for the control valve, because here we see no data is given. So that means here we assume the GV equal to KV equal to 1. So that is the value of valve transfer function. So we know that the GV equal to KV equal to 1. So we complete that one transfer function. So the GP is provided here. So we just use directly. GP equal to 5 over 5S plus 1. Then, in this case, the remaining transfer function is your GM. So for the GM is based on the measurement or transmitter data. So this you can see from the table here, measurement transmission data. So this refer to your GM. Similar like the set point transmitter, it also given in the form of the table. So this means in this case, the GM is related to the KM. So here the GM equal to KM equal to out divided by in. So 20 minus 4 divided 16 minus 0. So you have delta output over delta input. So you have the KM equal to your output will be 20 minus 4 divided by 16 minus 0. Or if you put it like this, 4 minus 20, 0 minus 16 is also acceptable because it will give you the similar answer. So where this one you have 1, this one is also 1. So this means in this case your KM is equal to 1. So in this case, what I want to highlight, notes that the KM bar will not be equivalent to your KM. So please remember this, although you have the similar KM, but the presence of this part, the bar. So this value usually will be, you will have a different value because this one is for your set point transmitter. And this one is for your measurement. So it's a different thing. So please do not assume your KM bar is equal to KM. Normally in some cases we provide the same value. But in this case, normally the term is different. One for the set point transmitter and another one for your measurement. So based on this, we already use all of the data. We use the GP, we use the measurement transmitter data, we use the set point, we use the control valve. The only missing transfer function is your disturbance transfer function. So for this disturbance, you will not use for set point changes. Because in the set point changes, this is your equation where the y prime s equal divided by y prime SPS equal to Km bar GC GV GP divided by 1 plus GM GC GV GP. So no GD here because this one is for the set point changes. So this means please do not add the GD inside the equation. So this to indicate either you understand the problem or not. Because sometimes based on my experience, student will take a look or what we are going to do with this GD. So they just include inside the equation where that approach is clearly wrong. So now we have all of the transfer function. The next step concerns with the substitution inside your equation. So we have y prime SPS equal to Km bar GC GV GP divided by 1 plus GM GC GV and GP, where the Km bar is equal to 4. So we include all of the transfer function. Multiply with the GC is KC. GB is equal to 1 and your GP 5 over 5S plus 1 divided by 1 plus the GM is equal to KM. So equal to 1, the GC, KC, the GV 1 and the GP is 5 over 5S plus 1. So you have substitute all of the transfer function inside the set point changes transfer function. So the next step, since this one is little bit simple, you can do the expansion and simplify the equation. So this will contribute into 4 multiplied by 5, you get 20 kc. And then divided by 5s plus 1 plus 5 kc. So you have this form after simplification. Let's say if you don't want to do the simplification, you don't want to do the expansion, it is also acceptable. No problem. So either you can remain like this, 20 kc 5s plus 1 divided by 1 plus 5 kc 5s plus 1. So if you want to remain like that, it's also acceptable. No problem. So this is the form. Either you expand, you simplify it, or you just do the simple expansion and leave as it is. Any question? So if you don't have any question, that means this is the answer for question A1, proportional controller. It just asks you to derive the closed loop transfer function. So the derive here means you use the standard set point changes equation, you replace the value, then you try to do the expansion or simplification. So now, so for the question 2, 3, 4, you will do it later. And then I ask you to complete the question B. Here the question asks you to calculate the offset. Calculate the offset of a closed loop response to a unit step change in the set point using P controller, where now the value of the controller gain is given, where the first one you need to calculate Kc equal to 1, then later on you substitute the Kc value to 10 and calculate again the offset. So for this part, we recall what is the offset equation. Offset equal to y prime SPS minus y prime sp infinity minus y prime infinity. So this is the standard offset formula, where normally it is in the derivation form. So we have this offset calculation. Now, what we want to do is how this equation that we obtained before can be used. So let me copy the equation. Okay. Now, based on my survey from your exercise, from the one that you submit to me, okay, there will be some confusion over here. So this is the thing that I would like to clarify more. So for this part, we have the y prime sp infinity. Y prime sp infinity minus y prime infinity. So how to get the value for both? So firstly, we go for the y prime sp infinity. So in this case, y prime sp infinity is based on the step change. Based on the step change for the set point. So here the information given to you is a unit step change in the set point. So a unit means the y prime sp equal to 1. So you don't need to use the information set point from here. Although this one you have the set point, but you don't need to use it. Because here we base on the given statement. Because I found out some of you use this value, which is not in accordance to the given question. The question clearly state that a unit step change in the set point. So this means you need to use the given information. So for this part, the y prime sp is equal to 1. So meaning that the y prime sps, when you try to do the Laplace, the 1 over s. It's like that. So for this part, we have the following equation. So now we have the y prime sp. So this means we can substitute this equation to here. Or if we try to rearrange it, y prime s equal to y prime sps multiply with the 20 kc. 5s plus 1 plus 5 kc. All right. So we have y sps equal to 1 over s. So this means this part can be substituted into here. And then we know that the initial value, the controller gain has been given where kc equal to 1. So for kc equal to 1, for kc equal to 1, then your equation y prime s equal to 1 over s. Multiply with the 20, multiply with the 1, 5s plus 1 plus 5 multiply with 1. So we get that y prime s equal to 1 over s multiply with the 20, 5s plus 6. 1 plus 5 is 6, so you get 20 over 5s plus 6. So in this case, we have the y prime s. The one that we want to have is y prime infinity based on the offset calculation. So meaning that we need to use final value theorem. So if you take a look on the slide given to you last week, the final value theorem indicate that if we want to find the y prime infinity, we set the limit s become 0. When you want to find the y prime at time equal to infinity, the limit set s equal to 0, where you need to multiply s multiply with the y prime s. So this is the formula. So s is your Laplace multiply with the y prime s expression. So this y prime s needs to be substituted into here. So this contribute to the y prime infinity limit s approaching 0 equal to s multiply with the 1 over s multiply with the 20 by s plus 6. So this contribute to cancellation of the s. And then 5s plus 6. 5s here, the limit s becomes 0. So the 5s becomes 0. So you have 20 over 6. In other words, in this case, y prime infinity equal to, so 20 divided by 6. You get 3.33. So this is the value of your y when kc equal to 1 at time equal to infinity. So now, based on the offset calculation, it is y prime sp infinity minus y prime infinity. So offset equal to y prime sp infinity minus y prime infinity. Where the y prime sp infinity here based on the a unit step change. So that means the y prime sp equal to 1 minus y prime infinity is 3.33. So you get 1 minus 3.33, you get negative 2.33. So this is your offset value. Any question? You can check your answer. They say I'm doing it wrong. You also can correct it, no problem. So in this case, what is mean when you have negative offset? So it's like this. So if we try to sketch it, y versus time. So where the target value is your set point. Set point represent the value that we want to maintain. So let's say this one is your set point. So this is y prime, this is the equal to 1. So this is 1, the value that we want to maintain. The one that you get is 3.33. The y prime infinity, you get 3.33. So meaning that the 3.33, let's say at this point. So your graph is like this. The value that you want to maintain is 1, but you get 3.33. So this means the value exceeding the target. The value you obtain exceeding the target. So this what is mean by offset. Offset negative 2.33. If you have positive offset, that means the value obtained is below than the target. In this case, the value is higher than the target. So you get negative offset. So that's what it means. So this indicate that when Kc equal to 1, your process response is exceeding set point value. So that means it is not good lah. The best or the good controller must able to maintain the process at set point. So that means if you get offset 0, your controller is okay. If your offset is not 0, then that means you need to have further improvement. So that's why in this case, you need to calculate when your Kc equal to 10 and see what happened. So here we just repeat the step. So let me copy this one. So now we repeat for the Kc equal to 10. So now Kc equal to 10. So you get 10 here, 10 here. So the equation 20 multiplied by 10 will be 200. 5s plus 1, 5 multiplied by 10 will be 50. So you get 51. So based on this, 200, 51. So the value now 200 divided by 51. You get 3.92. So here, based on this, the offset now 3.92. So 1 minus 3.92, you get negative 2.92. So this is the new offset when you try to calculate using Kc equal to 10. KC equal to 1, offset equal to negative 2.33. KC equal to 10. This offset indicate that you have negative 2.92, which is still not okay, because our objective is to achieve zero offset. So for this part, by increasing your gain, it's not helping the case. Still you get large offset. The value still over predicted because you get negative offset. So I let you to check. If I did some mistake, just point out so for me to correct it. So I open to any question that you may have.
Doctor, um, Doctor.
Yes, please. Yeah.
Actually, for the question, right, after we calculate the offset, is it necessary for us to draw the graph also?
Okay, it depends on the question. In this case, it's not necessary. For this part, I just draw it just to show what is mean by the negative or positive offset. So for this part, I just want to illustrate. If you get the offset value, what is mean? So for this part, you can see that our target is 1. So the ideal case supposed to be your y prime should be at 1 also. But here you get negative offset. So when negative offset, this means your value exceeding the target value. So that's why I illustrate this diagram for your understanding. If in the question they ask, then you just need to draw like this, to sketch like this.
Okay, understood, Doctor. Thank you.
So now we already try two value, Kc equal to 1, Kc equal to 10. But for both cases, we get negative 2.33 and negative 2.92. So that's why I ask you to try question D. So can we get zero offset for using P controller? So this is the question D. In this case, the Kc is not given. We need to find with the value of Kc that will produce zero offset. So how to solve it? So let's use the original equation. So this is our original equation.
Doctor?
Yeah.
Yeah, doctor, I have a question. If the y infinity equal to 1 is not given in the question, so how, if it's not given, how should we proceed, and how should we proceed the question?
It is given in the question, this one.
No, if it is not given in the question, in the
Oh,
upcoming
it's
questions,
not
if it's not
given.
given,
Then you
yeah, how
can
should we calculate it?
you specify your assumption.
We have to always assume it as 1, or is there any value?
Any value that you can assume. When the question does not provide the value of unit step change, then you can put any value. Of course, the easiest one is 1. But if you
Okay,
try
okay,
to
doctor.
use 2, 3, 5, then it's also acceptable, no problem.
Okay, doctor. Thank you.
All right. So again, we want to solve question D. So we still use the following problem. So this is the question. Let me put in the new paragraph. Okay. So now we want to find what is the Kc value that contribute to 0 offset. Offset equal to 0. So we know that in this case, offset equal to y prime sp minus y prime infinity. All right. So the offset now is equal to 0. So we know that based on the given statement, the y prime sp infinity we use by default, which is equal to 1. So meaning that in this case, the y prime infinity must be equal to 1. So 1 minus 1 equal to 0. So here that's mean our equation, we know that y prime s equal to y prime SPS multiply with the 20 kc. 5is plus 1 plus 5 kc. All right. So this equation, y prime s equal to y prime SPS is 1 over s. Multiply with the 20 kc. 5s plus 1 plus 5 kc. So we just use the y prime s. Why we want to use that one? Because the final value theorem. So according to final value theorem, y prime infinity s approaching 0 equal to s multiply with the 1 over s multiply with the 20 kc. 5s plus 1 plus 5 kc equal to 1. This one. So y prime infinity must be equal to 1 in order to make sure you get 0 offset. So we put the final value theorem equal to 1. So in this way, it will contribute to the 0 offset. So you have the value of 1 here. So we want to solve this problem. We know that the s will be cancelled. This part will be cancelled. This part also can become 0 because s approaching 0 according to the final value theorem. So that leaves us 20 kc divided by 1 plus 5 kc equal to 1.
Dr. Nyewood not responding.
What?
Tak. Tadi Dr. Nyewood dia lag.
Oh, the lag. Oh, sorry. The one I cannot. I didn't notice. So now it's working.
Yes, doctor, it's fine.
All right. Sorry for the maybe some internet connection. So now based on this, the s can be cancelled. Based on the final value theorem, the s multiplied with the 1 over s, it will be cancelled. The 5s in the denominator will become 0 since according to the final value theorem, s approaching 0. So that means this equation leads to the 20 kc over 1 plus 5 kc equal to 1. So we try to find the value. Let's say here you can expand, rearrange the equation. 20 kc equal to 1 plus 5 kc. 20 kc minus 5 kc equal to 1, where 20 minus 5 is 15 kc equal to 1. So kc equal to 1 over 15. So you get 0.067. Can you check the answer?
Yes, doctor, it's 0.07.
Okay. So this indicate that when I use Kc equal to 0.067, Kc equal to 0.067, you will get offset equal to 0. So when we try to do the sketching, this is your dash line, which is equal to 1. So you get the response like this. Offset 0. When Kc equal to 0.067. So this means it is this controller able to maintain the process at desired set point when Kc equal to 0.067. So if we take a look at the question again, determine new controller setting for the P controller to successfully eliminate the offset. Eliminate the offset, this means offset must become 0. New controller setting means what is the value of the Kc. Based on this new control setting, justify whether the P controller have a realistic potential to fully eliminate the offset or not. So you need to do the justification. So based on this, you get Kc 0.067, which is positive Kc value. Positive value of Kc. Then that means the value is logic. Logic and reasonable. If you get, let's say for some cases, you get Kc negative. Kc negative 1, for example. Then you cannot use that value because normally the proportional gain value must be positive. It cannot be 0, it cannot be negative. If you put Kc equal to 0, that means no controller lah. There will be no controller if you put Kc equal to 0. But if your Kc is negative, it will give a negative effect. It will provide unstable system. So I put here negative Kc should not be used. Provide unstable system, which is undesirable for chemical process. So that is what it means. So in this case, although the value is too small, 0.067, but still it is applicable to ensure the offset become 0. So that is the answer for question. What is the question? Question D.
Doctor,
Yes.
is it same to use for using the small letter y and capital letter Y?
It's okay. This is
Okay.
normally the one I don't mind. If you use small letter or the capital letters, both are acceptable.
Okay, thank you, Doctor.
Okay, I will share this discussion in the Google Classroom later. You can do the further revision on that. And in addition to that, I would like you to complete all of the question. For example, here I already complete A1. A1. So you complete the A2 using PI, using PID, using proportional derivative controller. And then you complete equation C. D has been completed, and lastly is the E. E. If you able to answer this question, then I will guarantee in the final exam, you don't have any problem relating to this question because this tutorial cover everything for the closed loop control, which represent one question in the final exam. Of course, there will be no additional mark for completing the tutorial, but please, I strongly suggest for you to do the exercise. Once you complete it, you can submit to me for checking. I will mark your exercise and return it back to you for your revision. So, any last question before we end our session for today? So, if not, then I think that's all for our class today. I really appreciate your effort trying to do the exercise, and for me it's a good thing for you to practice, and hopefully you gain something during our discussion today. And please, based on my recommendation, complete the remaining question. So with that, again, I thank you for your cooperation, for your response and your commitment. I see you again next Wednesday because we still have one holiday on Monday next week. So thank you again. Have a nice day. Class is dismissed.
Thank you, sir.
Thank you, doctor.
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 Thank you, doctor.